accelerated our move into that realm. But I want to caution that really it's not about a hypersonics race. We aren't developing hypersonic strike systems to go against adversary hypersonic strike systems. We're developing hypersonic strike systems because of the unique warfighting attributes of range, speed, maneuverability, and therefore survivability, as you mentioned, and lethality. Mm-hmm. So those four attributes really provide transformational warfighting capability that allow us really to address a broad set of threats in the aggressive A2AD environment that is being developed and fielded by the great power competitors of Russia and China currently. So our suite of weapon system is really defined not in comparison with others' weapon system development, but in comparison with what mission capabilities and target sets we need to defeat to ensure that we have battlefield dominance for decades to come.
Well, and I want to turn to George on this, but first, would you talk about the unique set of different targets of objectives that the U.S. has? It differs from Russia and China a little bit because they, as I understand it, are building hypersonics capable of carrying a nuclear payload, and so there's not as much precision that's required in terms of what they're developing, because a nuclear bomb, you can hit a very broad target and still have an impact. The U.S. has given itself a somewhat harder challenge of developing hypersonics that can hit a strategically precise target, a target that is a precision target. So can you talk a little bit about how the U.S. challenge of creating a precision system is a little bit different from creating one that can carry a nuclear weapon and thus does not need to be as precise?
Yeah, I mean, I think you characterize the difference in guidance requirements depending on the size of the warhead, and certainly a nuclear warhead is on the far right extreme of size of warhead. The Chinese and the Russians have stated that they are developing both conventional and nuclear systems, so they're working both sides of that equation. We are focused on conventional systems in our portfolio and regional systems, and so there is a challenge associated with guidance and control and getting to a target set, and that challenge is really how well we can strike a given target, and it's not just about guidance of the missile, it's about the whole kill chain and fire control loop necessary to be able to know where that target is and then precisely locate it. So there are significant challenges, but we're working those challenges across the entirety of the kill chain as well as within the weapon system components.
Okay, so George, give us a sense of how this competition looks internationally between the United States, Russia, and China, and also the other players in the hypersonics field. What are they contributing to the current state of the art as you see it?
Well, I think Mike answered all the questions that you had pretty well, so I don't know that I have much to add to China and Russia. Mm-hmm. And also on the U.S., I mean, he characterized all our needs, et cetera, excellently. So what I can do is maybe talk a little bit more about the rest of the world. And there is a lot of indications are that many nations are very interested in hypersonic weapons for some obvious reasons, and Mike summarized some of these. They want to be on par with some of our capabilities, Russia, China, and the U.S. They're a bit behind, is what it seems like, but there's also international cooperation, and some of these nations are making progress. I mean, we hear about through the news about some progress, in Japan, and as Mike mentioned, also Australia is working on. India has been working on it, and there's been some claims that they have some system that are nearly complete. They've been cooperating with Russia, so there is interest in the international world, and. One thing that we wanted to do, we're trying to see, we wanted to come up with some ways to make sure that these weapons are not proliferated beyond, first of all, the three major nations that Mike mentioned, the U.S., Russia, and China, and then France and India. I mean, they're doing a lot of organic, they have organic capabilities to be able to develop some of these capabilities and potentially an integrated system. However, the rest, it's very expensive, very difficult, very challenging to develop these systems. So we see some opportunities where, controlling some critical technologies might be able to at least slow down the development of these, at least the acquisition of these weapon systems by other nations. There's a big issue with, as I mentioned earlier, dual use. Some of the nations are suggesting that they want to use hypersonics for commercial, and Mike touched on this a little bit. But that's, in our view, that's going to be a long-term thing. I mean, we don't see, based on history at least, we can go back and look at our commercial transports. The Concorde was a great plane, but it didn't last very long. It was very expensive. The business case wasn't quite there initially. They might have made some money later on. So imagine taking this and put it on hypersonics. It's going to be many, many, many years before we see at least commercial airliners.
Mm-hmm.
So from that point of view, we see there's a lot of interest in the international community, but a lot of challenges also. So hopefully we'll be able to control some of the proliferation.
Okay.
George makes a really good point, Patrick, and I'll just add that the airliner problem is a pretty difficult problem. It's a pretty harsh environment, and getting people to be protected and reliably protected from a commercial airline perspective is I think many years and several decades down the road. I think the more near-term commercial application is looking at a system that gives you advantages for low-cost access to space. In the commercial realm. So when we start to talk about these large constellations of satellites, if we can come up with a two-stage, or even back in the X-30 days, we were looking at single-stage to orbit capability for a reusable access to space capability, I think that's probably the nearer-term commercial application.
So on the commercial applications, and there are some commercial players that have talked about their interest in this field. SpaceX is one. Already taking over more and more of the private space market and the market for launching things into space on behalf of the U.S. military, and also now taking human beings into space, the first private space company to take human beings into space. They've outlined hypersonics, both travel and, of course, for space access as goals, one being much more proximate to them. But one of the keys to, I think, making a business case for hypersonics for space is this question of reusability, right? And on this idea of a hypersonic vehicle that doesn't just become worthless after the first time it's used as a missile would, but can be used over and over again, more like a conventional craft. Where are we right now? I understand that the Pentagon has conducted something of a study on reusability in hypersonics. So what's the thinking there right now from the Pentagon, and what is the strategy?
Well, from a reusable perspective, we are obviously in the near term looking at the application of hypersonic technologies to reusable systems for military missions. Mm-hmm. And so we are doing some studies and looking at various technologies to evaluate and then develop the necessary enablers to have reusable hypersonic systems. I mean, the key enablers, some of them are very similar to the weapons, like high temperature materials and thermal management. Some you take a different approach, like propulsion. There's a tendency to want to use turbine-based combined cycle propulsion system as opposed to rocket-based boost glide systems or pure scramjet rocket-boosted scramjet-powered cruise missiles. You want more of a reusable propulsion system, so you go to more the turbine-based combined cycle system. So we are looking at the enabler technology set as well as potential future applications and configuration designs.
So you started these studies. When did you start the studies looking at reusability?
Oh, they've been going on off and on for a number of years, and so as I mentioned, even today the reusable system is more in the phase one technology development and maturation stage of a four-phase strategy. So we've been looking at reusable hypersonic systems for quite a long time, and again, in fact, if you look back into the 80s and 90s. The whole nation, whole hypersonic nation, was focused on the X-30 and the National Aerospace Plane Program to have a reusable single-stage to orbit capability for that X-30 program. So we've been working it for quite a number of years.
Okay, and in terms of you sort of touched on a couple of them, but I want to elaborate a little bit on the emerging technologies that are going to enable reusability. You'll need for coatings. New breakthroughs in, I guess, chemistry and different ways to approach the development of new materials. I imagine 3D modeling and possibly artificial intelligence. Can you tell us a little bit about the new and emerging technologies that are creating new realities for reusability right now. I'll turn that to you.
George, you want to start, or?
So yeah, I can say a couple of words here, but Mike, you probably have a lot more insight into this. So I think you hit on it, Patrick, in terms of the materials. Materials obviously is one of the major, has been one of the major barriers in terms of reusability. And as we know, the challenges we've had in the past, if you think about the space shuttle, et cetera, it's always been a challenge, especially once you go beyond a certain threshold in Mach number, when you start reaching the higher Mach numbers, higher hypersonic region. So that's one thing in terms of, and Mike touched on it also, in terms of how you integrate the system, the propulsion, kind of propulsion system you want to use. And we know some of the commercial companies nowadays are able to reuse, kind of rocket powered. So some of the systems are, we know SpaceX, obviously, they're stage one, or they're actually are able to reuse it. Yeah, so I think the material is one of the major one, and how you integrate the overall system from a propulsion point of view, where you use combined cycle engines and such. That's going to be some of the major challenges. Mike, I hand it over to you. You probably have more insight than I do.
Yeah, I think between the two of us, we've talked about it. Really is materials and propulsion from a technology perspective that get us where we need to get to. But George touched on something that's really, really important is in order for these systems to be viable and what we call closed, in that they can, you can build a vehicle system that accomplishes the mission that you desire within a certain weight and basically cost constraint. There's a real system integration problem that you really have to optimize. So we do things like multidimensional optimization to make sure that we are fully optimized in the way we integrate the various elements of these systems. And it's really important to do that because it's a hard problem. We're flying on the margins from a thermal management perspective. Boundary layer transition is hugely important and can dramatically change the thermal management requirements and materials requirements for the vehicle. What subsystems you put in and how you optimize the subsystems is hugely important. And then the ability for the engine to be efficient and robust and reliable is going to be a key driver in the way the whole system comes together. So that multidiscipline, multidimensional optimization is going to be a key system driver in order for us to realize future hypersonic systems. There are a number of, one thing that I have found very interesting since I'm taking this job is the number of small companies and even at this point venture capitalists who are interested in trying to leverage the capabilities of hypersonics for various applications, either the business models associated with developing reusable hypersonic systems as test assets, as well as for the ultimate mission applications we talked about, either whether it's commercial hypersonics for future passenger applications or access to space. So there's a pretty diverse set of players. It's not just the big guys when you start talking about reusable hypersonics. And so it's an interesting ecosystem, if you will, that's developing in that realm.
So I want to turn back to that after a second, but first, one of the things that's very different in the year 2020 from the way, for instance, the Concorde was designed a long time ago, is there's much greater availability of compute. There's much better sense of how to, in a virtual space, create scenarios and simulations to help the design process, where you can, I know that this was a big effort from former Undersecretary of Defense for Research and Engineering, Mike Griffin, was to create new opportunities to use virtualization to design things in a virtual space better, more realistically, more credibly before you take it to the next stage. And that way you get done with a lot of the experimentation and you can solve certain design problems before you even start encountering them in 3D. So I wonder if you can talk a little bit about how the design of these things has changed from a few years ago as a result of new tools, like a lot of compute, like new data science and regression tools, things like that, how they're impacting the development and the design and that optimization problem you talked about of developing these things.
Yeah, it's interesting. I look back at the, this is like my 40th year doing this stuff, so it's been around the block a few times. And back in the days of the National Aerospace Plane, the holy grail was computational fluid dynamics. Because we had computational fluid dynamics, we could design the vehicle without going and doing a bunch of flight tests, and we would fly just to validate the codes. And the notion back then was we had come far enough along in turbulence modeling to where we could understand the transition in turbulent and laminar boundary layer effects on the overall vehicle design. It turns out we weren't quite as smart as we thought. And I think that in particular with turbulence modeling, I maintain it's pretty much chaos theory, and so we've gotten much better at modeling boundary layer transition, but we're still not very good at it because I think we still don't understand all of the core phenomena associated with it. So there's a lot of room for advanced modeling and simulation tools. I just earlier this week I sit on the board of directors of the Hypersonic Vehicle Simulation Institute, where they're developing modeling techniques and some very, very advanced modeling techniques that will help us design future reusable systems. And it will be absolutely essential to have those tools and have them continue to mature. But it really comes down to flying. The hypersonic environment is very difficult to simulate on the ground. Wind tunnels tend to be noisy and that they introduce turbulence that are specific to the facility as opposed to being representative of flight in the atmosphere. So those effects can be very, very difficult. It's very hard to simulate the proper energy conditions or enthalpy conditions in a wind tunnel to get to the very high Mach numbers. I mean, we're looking at systems that are flying not just at Mach 5, but anywhere between Mach 5 and Mach 20 within the atmosphere, and that's a pretty stressing environment. So you really need to have a robust modeling and simulation environment. You need to have a very robust set of ground test facilities that are as representative as they can be of the flight environment, and then you got to go fly. And flying is not cheap. Historically, we've been on a pace of like one flight test every couple years for the last 10 or so years. We're going to fly in our portfolio of programs over 40 times in the next 4 to 5 years. And so there's a lot of flying that we're needing to do to move through that those phases of maturity to get to our systems, get to the point where we're fielding systems that are viable. And that's just for the expendable weapon systems. Once we get to reusables, it'll even be more intense.
So I want to take to George with that in just a second. But first, when you talk about the tremendous burden of flying these in real space and how important that is for design, one of the things that former DARPA director Dr. Stephen Walker, a longtime leader in the Defense Department for hypersonics development, that sort of thing, one of the things that he brought up a couple of years ago, I know Mike Griffin was concerned about this as well, was a gap in test ranges that existed between the United States and China. We had only really one place where we could conduct the sorts of tests on hypersonics that you've described, where you can actually fly them and see what it's like. I know that there's been a little bit of progress there, partnering with University of Texas to develop new testing ranges. But how do you describe that gap that they mentioned? Has it been addressed? Is there still a range gap in terms of places, huge areas of land to actually see whether or not these designs are working? Do we still have that?
Yeah, I mean, there are some charts that exist, and I'm not sure whether they're open or not. But you can see the U.S. hypersonic facilities over the last 40 years, and basically it is a steady decline in the number of facilities. And then you look at the investment that China has made over the last decade or decade and a half to build facilities, and it's very, very clear that there's a strong national priority because they've made a huge investment in infrastructure in China. But again, it's not about how our facilities compare to China; it's how our facilities meet the needs that we have. And so there are new facilities that we've built. We've built a mid-pressure arc down at AEDC, and that mid-pressure arc is a vital resource for ground testing of materials in a high-temperature environment consistent with hypersonic flight. And we mentioned speed and maneuverability in hypersonics, and it's really important. But that speed allows us to fly in what we call a near space regime, where we don't typically fly other than to fly through it, right? When we re-enter, we fly through it. When we go to space, we fly through it. But between about 80,000 feet and about 150,000 feet, there are no systems that really operate in a sustained flight manner within that part of the atmosphere. And so, our facilities need to replicate that part of the atmosphere. And so we're in the process. The Test Resource Management Center has responsibility for the national infrastructure. And they have a very significant investment strategy to build ground facilities, add capability to existing flight test ranges, and then develop additional future flight test ranges moving forward. Right now, our primary flight test range for long-range hypersonic capabilities is out in the Western Pacific and, out of the PMRF range and into Kwajalein, those kinds of flight corridors. We also fly out of the West Coast and fly west over the Pacific to places like Point Mugu and Vandenberg and Edwards. But all those ranges result in flight into the ocean. One of the advantages that both China and Russia have is they have very, very large land mass where they can actually fly over land and have land-based termination for their systems, which can have some obvious advantages. So we're looking at what can we do to resurrect some of our longer-range land bases within CONUS. I'm looking at working with Australians and looking at Woomera, and then even have had some discussions with Canada to look at options for overland ranges, as well as looking at exploring over land range capability in the Atlantic. I mean, currently the Navy flies very long-range missions associated with Trident out of the Atlantic ranges. So we're looking at how do we piggyback on that capability and leverage those assets as well. So we're looking at significant expansion of what we're doing in the test ranges. We're looking at investing in the infrastructure to where we can replace the maritime-based telemetry and flight termination capabilities with airborne flight termination capabilities, developing something called Range Hawk, where we take a Global Hawk or a family of Global Hawk systems and we fly those in conjunction with the flight test. And that gives us great flexibility as to where we test. So that opens up possibilities as well. So TRMC has been great. They started investing in it before the modernization priority was established. They started investing in it in the 2015 timeframe. That's why we have the H2 ARC right now. We'll build another ARC because the demand signal is so high between us, Missile Defense Agency, and nuclear modernization. So we're really making that huge investment in test and evaluation, both from ground and flight test perspectives.
All right. So over the Pacific, potentially partnering with Canada. When and where do you imagine this flight test where you have this constellation of Global Hawks that are collecting data and kind of observing a flight test? When does that happen and where? I've never heard of that.
That's a capability that we're working on now. We've got the Global Hawks procured. We're modifying them now with the proper sensor suite. And over the next couple of years, we will fly those systems in the shadow mode. And then get reliability data, and then eventually be able to fly them as a primary means for telemetry.
Interesting. I feel like that's news. So, George, tell us a little bit about the study that you did, taking into consideration all of these things that are happening, these new breakthroughs in virtualization, the still hard problem of flight testing, and the hard problem of chemistry for coatings, et cetera. What was the determination that your study reached in terms of the commercial viability of hypersonics within the next decade?
Again, I'm going to say that Mike summarized it pretty well. We've made a lot of advances in CFD, as Mike mentioned, but as he also mentioned, we weren't quite as smart as we thought we were. A lot of challenges flying hypersonics. I mean, we have, and so we identified actually modeling and simulation and ground testing as some of the major challenges that barriers that would actually enable us to potentially control some proliferation of these weapons from point of view of organic development. But having said that, there's a lot of advances being done. I mean, the university are working on this, but it's going to be, and I don't know what's going to happen in the future, but based on what we understand right now, being able to to predict, things like boundary layer transition for all kinds of different flight conditions is going to be very difficult. Wind tunnels have very limited capabilities from the point of view of how long you can fly them, and we're building new wind tunnels, for quiet wind tunnels and such. But you can only use them for so long. They don't really, the fidelity by which they represent the atmosphere is not very high, right? They're almost ideal conditions. So it's going to be very difficult to completely replace flight tests with just I guess you want to call it digital engineering or whatever. But it's not. We don't see it, at least anywhere in the near future, being able to completely replace that. There are a lot of things you can do. You can do potentially some parametrics. You can do some sensitivity analyses and such. But at the end of the day, you're going to have to test, and flight test is probably what you're going to end up having to do for the hypersonic types of vehicles. And again, the more data you collect, you can anchor models, you can do things, you're going to get better and better. Mm-hmm. But again, at the end of the day, I think it's like Mike said, you're going to have to fly these things. And I think you're saying the same thing. Yeah. I don't know if I answered your question here.
No, I think that outlines the problem very clearly. So let's take some audience questions right now. We have a couple. Hypersonic weapons are no longer marked as the DOD's #1 priority. Has this impacted the DOD's work on hypersonic weapons, and is this expected to make a difference in budget allocations? So for a bit of context, the Defense Department 2017 laid out a number of technological modernization areas, just big emerging tech that they wanted to put money into, and among them was hypersonics, as well as quantum computing, artificial intelligence, joint all-domain command and control, et cetera. And I think that very recently, microelectronics has replaced hypersonics as what the Defense Department described as their #1 priority. So has that impacted or affected the budget allocations for hypersonics, Mike?
I will say it has not impacted it, and I'll say this because this is the department position, not just because I'm trying to make our team look good. But the idea was that hypersonics was a department priority. We needed to do something significantly different than we were doing in order to accelerate from where we were. So the department placed #1 priority on hypersonics. If you talk to Dr. Lewis and even Mike Griffin before he left, the reason why hypersonics has drifted down a little bit in the priority, behind microelectronics, mainly is the fact that we're on a good path, that we've kind of got the ship moving in the right direction. We've got great momentum. Our budget since 2016 has gone up by a factor of 10. In 2016, we were investing on the order of between $300 and $350 $1 million a year. This year, we're on the order of $3.2 to $3.5 billion. So our annual budget has gone up by a factor of 10. And then over the 5-year defense plan, we've gone up dramatically. Just between FY19 fit up and FY20 fit up, we went from $5.6 billion to right around $13 billion. And then we'll be on that pace again for 21. And then the department has made a significant push to move us from phase 2 to phase 3. And I think you'll see that in future budgets. So we've got great momentum. We've accelerated once, going from 19 to 20 to kind of get from a phase 1 environment to a phase 2 environment. We've laid a plan in place to accelerate a second time to go from phase 2 to phase 3. And we're working the groundwork through what we call an industrial-based war room to be able to make sure we're on pace to move from phase 3 to phase 4 and ultimately put in place programs of record and capability phasing plans to get us robust capability for the future. So I couldn't be happier with the energy and importance the department is placing on hypersonics, and I think the budgets currently and in the future will reflect that.
And what's the target date for a deployable program of record? I'm trying to remember.
Well, our portfolio right now is focused on fielding capability, both from land, air, and at sea in the mid to late or early to mid 2020s. So okay. We'll have capability fielded in all 3 modalities by the mid 2020s.
Okay. So related to that 13 billion that you described for defensive means, on the defensive side, where are we?
That was our full portfolio in hypersonics, not just defense. In fact, most of it is on offense.
Right, but I mean, in terms of the 13 billion that you talked about, comma, on the defensive side.
Okay.
Yeah, sorry about that. Right. I can't punctuate in webcast. It's very hard. On the defensive side, where are we on a complete kill chain by satellite means?
I won't talk to the details of the kill chain. I'll mention that we universally recognize that the weapon is only part of the equation when it comes to fielding capability, and you have to have a detect, control, and engage sequence to realize capability. So we are working the kill chain pretty significantly. If you look at the Space Development Agency, the Space Development Agency was really established to create a robust space-based architecture for proliferated LEO and MEO capabilities, for having custody layers and transport layers that where the requirements are primarily driven by persistent global tracking of hypersonic threats for defensive purposes, as well as ground tracking of high-value mobile targets for hypersonic offensive purposes. So we are driving requirements very, very substantially into the space architecture, and it's being developed with the hypersonic application and the capabilities enabled by hypersonics as a primary requirements mechanism.
And you're still looking at a counter hypersonic capability that uses that space layer for tracking. You can watch the hypersonic as it maneuvers in space, and that way you don't lose sight of it. But the intercept, you're still imagining, happens from the ground, where you shoot something up and then you hit it from the ground, as opposed to, and this is something that the Defense Department had been talking about over the last couple of years, and I think it's talking about a little less now, trying to intercept the hypersonic missile from space using perhaps neutral particle beams, which I know they've shelved, possibly directed energy, or even a kind of missile launched from a satellite itself. Is that something that the Defense Department is still looking at, trying to intercept a hypersonic missile from space?
I don't really want to go into the full range of our, kill chain elements and what the opportunity space is we're looking at, but suffice it to say, we are looking at a comprehensive layered defeat strategy to look at how do you defend against adversary systems in all elements of the adversary kill chain. Okay,
we've got time for, I guess, maybe one more. And apologies, George, a lot of them do come in for Mike. Are the DF-17 and Zircon systems operational now?
I don't know that I've seen official statements in the public. I can just say the DF-17 was paraded in significant numbers at the last military parade the Chinese had, and the Zircon system is a capability that has been demonstrated by the Russians in a very operational context. So,
okay. And with that, we've got time for, I guess, one more, and we're not getting one in, but I have a question for everybody. Based on, and understanding you're speaking on behalf of yourself in this, so based on your own expertise and how you have perceived this technological landscape proceed over the last, in the case of you, Mike, decades, the prospect of manned hypersonic spaceflight using a maneuverable, like as outlined in the Defense Department strategy, eventually getting to hypersonic craft that can both go to space and also serve as aircraft, reusable aircraft for humans. What is your expectation of when that becomes a reality?
Wow, that's a loaded question. If you look at the X-37B right now, that is an unmanned system that flies into space, does its thing in space, and then re-enters in the hypersonic environment. What the difference is, it doesn't operate with sustained hypersonic flight within the atmosphere other than through re-entry. I think if you're talking about a manned system for reusable applications, I think we're probably talking 2040 to 2050.
Okay, very conservative, which is good because you're with the Defense Department. George, what is your estimation?
Yeah, no, I think it's, as I mentioned earlier, I think this is one thing that's going to be a while. I should add also, and I'm sure Mike is familiar with it. You might be familiar with it too. The Stratolaunch is looking at a reusable kind of hypersonic platform. They're talking about for testing purposes and such. So, but I mean, going from a remotely piloted vehicle to a manned vehicle is a huge step. And so I agree with Mike. You know, it's gonna be a while, 20, 30 years. Yeah.
I think we will have unmanned reusable systems much earlier than that. It's putting the man, and you have to decide for many of the applications whether it needs to be anything but unmanned, right?
Yep, absolutely.
Yes, we are but fragile bags of juice. And with that, it's time.
Hey, Patrick, I do see a question about the LRHW Army and Navy cooperation for CPS up there, and I think that's an important question that I do want to emphasize the response to, and that is,
please.
One of the things that we have tried to do in creating these modernization priorities and establishing principal directors for each modernization priority is the principal director is really responsible for the entirety of the department's effort in the particular modernization priority. Now, in some areas like microelectronics, it's huge. Cyber, it's huge, and so the scope is you really can't get your arms around that elephant all at one time. But for hypersonics, it's a relatively closed community. And what we've been able to do is really take that community and knit it together in a very cooperative and collaborative way. And there's nothing that demonstrates that better than what the Army and Navy have accomplished with the Conventional Prompt Strike program. Conventional Prompt Strike is a program that was run out of OSD, out of our office, executed by the Army and the Navy. We've had several very successful flight tests. The last flight test was completely successful. And 2020 marks the transition of that technology to the Army and the Navy. And while at the beginning they weren't really working very closely, we as a team have created a board of directors between the Army and the Navy, the Air Force, MDA, and OSD, and we've driven that activity to be highly integrated to where the Army and the Navy are in lockstep. General Thurgood, Admiral Wolf, and the Army and Navy team, respectively, are working to a common all-up-around missile that will both be a land-based and sea-based capability. And the team is working very, very closely together with responsibilities that are divvied up through a memorandum of agreement. And it really is a success story as to how you can integrate across the department towards a common but different end state. So I'm very proud of that team and the accomplishment and what we've accomplished. And so I do want to bring that up as a significant success story over the last 2 years.
Okay, thanks. I'm sorry I missed that one. So this has been great. I learned a lot. It's time to end the editorial portion here. I want to thank Mike and George for the conversation, and I want to turn the program over now to my colleague Lori Diamond, Senior Director of Defense One, and Dr. Thomas Boggs, Chief AI Architect for the AI and ML project at Leidos. So, Lori, over to you.